All right, guys. Good evening. So looks like today also we don't have any audience. So I hope you guys are, going through the YouTube lectures, YouTube videos. So anyway, what we will do is it's 7:02. We will start, and if there are, if you have any questions, you can come back again. So today's topic is going to be a little less. All right. Thanks, Krishna Kumar, for joining. So today's topic is going to be as turboshaft engine, and the numerical is very easy, and it should be easier for you guys to solve. So what I will do is I will solve one numerical, and also I will touch upon certain aspects of the turboshaft engine, and uh, yeah. So this will be our week 11. So we will meet one more time. Next week we will be looking at component matching, numericals for component matching, and that will be the final session. So if you have any doubts, I think this week or next week is the uh, right time to come and interact with me, and that should be able to that would be helpful for you for your exam. So I think your exam is also coming up probably in sometime in the third week of October. All right. So with that note, maybe I will start today's session. Let me check my recordings. All right. All right. Okay. So, as I said before, what we are going to do today is we are going to solve the turboshaft engine numerical. And we all know what we did this week. So this week we studied about turboshaft engine, single spool and dual spool turboshaft engine. Why we need turboshaft engine? What are these applications? What are the challenges and advantages of turboshaft engine? And yeah, so these are the things we studied about turboshaft engines. In addition, we also studied about prop fan engines, prop fan engines. Um, if you remember, we also touched about prop fan engines sometime in week 9. So, but we didn't solve any numericals, but we solved one numerical here in week 11. So, I think I think your problem is also the assignment 11 problem is also based on prop fan engines. So if you get an idea of how turbo shaft engine works and also how turbo fan engines works and turbo prop engine works, it should be straightforward to solve the numerical that is given in this week's assignment. All right. So what do we know about turbo shaft engines? So basically, uh, we were we started with turbojet engines, and in turbojet engines, our main goal was to get thrust. Now in turbo shaft engine, our main goal is to get the uh, power out of it. So we are not interested in producing thrust with this engine, but we are interested in producing power. So we will have a turbine, and from turbine, that could be directly connected to the load, or to connected to the electric generator to generate electricity. Uh, but we have to generate some power. So that is the whole concept of turbo shaft engine. We have to have uh, instead of thrust, we are interested in power in this engine. And this is we all know the applications of this engine is enormous. So usually these are employed at helicopter engines, where the rotors require some power, and that power is produced by these turbo shaft engines. And also certain industrial applications to run compressors and to run bigger machineries in oil refineries, other industries. They use turboshaft engines to generate power and electricity. So let's quickly go through the TS diagram. So I think we all are experts in this by this time, because we have been doing this for several engines for like 10 weeks now. So it should be straightforward for you. In turboshaft engines, we do not have a nozzle. Instead, one of the turbine is connected to the load, so we generate power. That's all. Other than that, it is similar to turbojet engine. And although in construction wise it is similar, but the operation wise these are a little bit different. Okay. Um, so initially you have air getting compressed in the inlet, and the if the turboshaft engine is uh, moving with a you know m naught or m infinity, we can say. Uh, and the next component that you have after inlet is the compressor 2 to 3, across which the pressure rise is happening. And then from 3 to 4, you have combustion chamber where you add fuel. So it's a constant, usually it should be constant pressure, but these are not ideal cycles, these are real cycles. So there will be pressure loss. And it will reach a maximum temperature of T04. And from 4 to 5, you have high pressure turbine, and this turbine work is used to run the compressor. Okay, so the main job of this high pressure turbine is to run the compressor, nothing else. And then you have low pressure turbine or free turbine, and across. So what you try to do is you try to extract as much as energy across this free turbine. Okay, um, and that is what we will do today also. We will try to extract as much energy as possible across this free turbine. We don't really worry about whether we need a high temperature or high enthalpy outlet of this free turbine, because we are not going to expand it in the nozzle, and we are not interested in thrust. So whatever it comes out of the turbine should be very low pressures and temperatures, such that you must have extracted as much as energy you can. Okay, so the whole point of turboshaft engine is to extract power out of it. Okay, so so today what we are going to do is we are going to solve this turboshaft engine, and it is going to operate at ground condition. In lectures we already solved this engine, but it was in the flying condition. So the Mach number was around 0.21. So the same engine, but if it performs in the ground condition, what is going to be the performance, how the performance is going to vary, is what we are going to see. And you will be quite surprised about the performance compared to whatever the flight condition that you got. Okay, um, let's look into the problem. So what you have is a turboshaft engine operating at ground condition. Ambient temperature and pressure is given. The compressor pressure ratio across this 2 to 3 is 9.5. Turbine inlet temperature is 1320 Kelvin, and the pressure loss in the combustion chamber is 2%. Fuel eating value is 44 megajoules per kg, and the total mass flow rate through the engine is 12 kg per second. Okay, and we also have component efficiencies. We also have burner efficiency, mechanical efficiency, gammas and C. Okay. Now, what we did in the lectures is for flight conditions. The load, the power of the free turbine was around 3.89 megawatts, and since the turbine and the connected mechanical efficiency has it has some efficiency, the power which was delivered to the load is around 2857 kilowatt, which is 3.857 megawatts. And the brake specific fuel consumption is nothing but your fuel consumption, the fuel economy, which is around 0.077 grams per kilowatt second. So you must have noticed here, till now we must have worried about thrust specific fuel consumption, because there our interest was in thrust. So our unit was also in grams per Newton second, or kilograms per Newton second. Now brake specific fuel consumption is all about getting so our interest now turned to power. So that's why our fuel consumption is also measured in terms of power. So it's grams per kilowatt second. And then you have thermal efficiency, which was 29.52 percentage. Now let's see how it performs in the ground condition. So, uh, so we all know how to solve this. So we first need to start component wise. First is inlet, and then you have compressor with a pressure ratio of 9.5, and then you have combustor, and then we know turbine entry temperature, which is 1320 Kelvin, and based on that we need to find the fuel air ratio. And uh, and then you have HP turbine, which is going to drive the compressor. And once you do the work balance across the HP turbine, you can find the pressure and temperature at the exit of the HP turbine. And then you have LP turbine or free turbine, which from which you will get as much as energy as power as possible and then deliver it to load. Okay, so this is the flow process, and this is how we are going to solve this numerical. So intake or inlet, we have uh, the air entering at pressure and temperatures of 100 kilopascal and 298 Kelvin, and the engine is moving at 0 meters per second. So in that way, the total pressure and total temperature is not going to change. It's going to remain same as 100 kilopascals and 298 Kelvin. So this we all know because it's in ground condition. So there is not much of a uh, calculation that we need to do for intake. The next component that we have is compressor. In the compressor, we have 9.5 pressure rise. So the inlet is 100 kilopascal. So you are going to have 950 kilopascal at the exit of the compressor. And you can notice that it is quite higher compared to what we solved in the lecture, because the ambient conditions were lower. As you go higher in altitude, the pressure and temperatures are lower, and because here you had 100 kilopascal, but in in flying condition you have 50 kilopascal, so that's why you have lesser uh, pressure. So there is something you need to note here. um, in the flying condition your compressor is operating at lower pressures, and in the ground condition your compressor is operating at higher pressures. Okay, although the pressure ratio is same. So the pressure ratio both in flying condition and also in ground condition is 9.5. However, the pressures across which this compressor is operating at the flying condition is lower compared to the uh, ground condition. So that has so the absolute value of that pressure across which it operates should have some effect on the uh, you know work done by the compressor, because these are not ideal compressors. It has an efficiency, right? Isentropic efficiency is there, and the isentropic efficiency directly deals with second law of thermodynamics. And also we know that not all the temperature ratios are same, right? So remember your thermodynamics class. So uh, yeah, so there will be some difference. Although the pressure ratio is 9.5, the work done by the compressor at the high during high pressures, operation under high pressures and operating under low pressures will be different. Okay, and so similarly we can find the temperature ratios. We just need to plug in the pressure ratio value, and the gamma for the air is 1.4 here, uh, and compressor efficiency is 84 percentage. So based on that you will get the temperature ratio. The temperature ratio again will be same as what we got in the lectures, because temperature ratios are not going to change. Only the absolute values of temperature will change. So because of that you will end up having a higher temperature of 618.21 Kelvin compared to what you got in the lectures. And the next component that we have is combustion chamber. In the combustion chamber, the burner efficiency is given 98 percentage, and the combustor inlet pressure is 950 kilopascal, and the combustor inlet temperature is 618 Kelvin, which we just saw. And uh, you can find the pressure losses. The pressure loss is 98%. Sorry, 2% of the pressure is lost in the combustor. So if you do 98% of the 950 kilopascal, it is going to be 931 kilopascal. So there is not much of a interesting fact here. And you can do mass and energy balance, and mass and energy balance will lead to fuel air ratio expression. And if you substitute all these numbers, you are going to get a fuel air ratio of 0.0217, which is less than what you got uh, in the flying condition. So you can think about it like this. In the flying condition, your exit temperature of the compressor is lower, okay, compared to combustion chamber, compared to ground condition. So now you wanted to heat it to the same temperature, which is 1320 Kelvin. So now since your exit temperature of the compressor was lower in flying condition, you have to spend more fuel, and that's why you see a higher fuel air ratio in terms of flying condition, whereas a lower fuel air ratio in terms of ground condition. Okay, so that's the differences that we are seeing here. And then what we have is HP turbine. In the HP turbine, as I said, we are going to run the compressor, and now you need to think a little bit. So if you do an energy balance, energy or work done by the HP turbine is equal to work done to the compressor, right? So if you substitute, if you substitute those relations and rearrange it, you will end up having T05 as this relation, so which we all know. Now, if you substitute these numbers, here is where it is going to get interesting. You have temperature to be lower compared to temperature you got in the flying condition. So this is kind of like a special case. You will soon realize it. So ideally, the inlet temperatures are higher. At the very end, for the inlet, the stagnation temperatures were 298 Kelvin, which is higher for ground condition compared to flying condition. However, the work done by the compressor in the flying condition was lower, and hence the temperature with which it has to, hence the amount of work the HP turbine has to give to the compressor was lower compared to uh, ground condition, and that's why you have temperature to be higher, which is around 10 like 1088 Kelvin. However, here, as I said, we are getting more uh, we are going to provide more work to the compressor because it is operating at higher pressures. Okay. um, yeah, so, and that is the reason you see that uh, the temperature with which the gases exit the HP turbine is lower compared to the flying condition. All right, let's move forward. Let's see what happens in the what happens to the pressure. So for the pressure, again, we all know from the isentropic efficiency formula, you can derive this relation. You will end up having a pressure ratio of 0.3398. However, in flying condition, you had a pressure ratio of 0.407. Okay, so this will lead to a turbine exit pressure of 316.33 kilopascal, whereas in flying condition you got 198.98 kilopascal. Although you cannot directly compare these two values because the entire pressure range has gone up because you started at 100 kilopascal. Here it started at 50 kilopascal. Okay. All right. So um, and the next component that we have is the LP turbine, or you can say free turbine, which is going to generate the power that we need. Okay, and let's say if we are trying to extract maximum power as power out of the LP turbine, and what is the so maximum we can do is to expand the air to the ambient condition. So you cannot go more than that. Okay, so expansion is nothing but during expansion the pressure is going to reduce. So whatever be your pressure, you can expand only till ambient conditions. You cannot go more than that. And uh, across this turbine, uh, this is the maximum pressure you can get. So for this maximum turbine expansion, whatever power you get is what is the maximum power you can extract out of the free turbine. So that's the reason we equate P6 to P ambient, and then we will try to find the temperatures at the exit of the free turbine. Okay, so this relation we already know, it's the isentropic efficiency formula, and what we are trying to put is we are trying to put this P6 to be P ambient. See, if you try to have P6 to be lower than P ambient, what happens is it cannot really expand. So there should be, if the gases has to flow, it has to flow through some process, right? So the pressure gradient is going to make sure the gases uh, move properly from one component to other component. Now, if you have higher pressure at the exit, the gases is going to rush inside, and if you have low pressure at the free turbine exit, the gases is going to rush inside, and you're not going to get uh, proper expansion. And because of these consequences, again you will be able to reach only ambient pressure. So this rushing in will happen until there is an ambient pressure, and hence the maximum power can be extracted out of this turbine could be upon expansion only till ambient condition. Okay, so once you expand to ambient condition, you can let out the air to go out of the, your engine. It's just a constant duct exhaust. So that is the thing. So we can only expand only till ambient conditions. And if you substitute that number over here, so here the P6 is P infinity. If you substitute that number over here, or maybe before that you rearrange this equation such that you want T6, because why we need T6? We are interested in finding power, and if you want to find power, it's going to be m dot Cp into T05 minus T6, right? So that is what is going to give me what is the amount of work done or power extracted from the engine. So that's the reason we need to find T6. Here we are not finding velocity of the exit. All these things is not our interest. So please remember that. So now if you substitute these numbers, the free turbine efficiency is 88 percentage, and the P6 is ambient condition, which is 100 kilopascal, and P05 is 316.33 kilopascal. Okay. Now, if you substitute these numbers, you would have noticed that there is a gamma H change from 1.4 to 1.33 because of combustion, and this will lead to a temperature of 818.05 Kelvin. Okay. Now, let's try to find out the power. So the power we got in the flying condition was 3896 kilowatts. Okay, which is around 3.9 megawatts, you can say. Now let's see what happens during the ground condition. So the power formula we all know, it's m dot Cp into delta T. Now m dot here is going to be m dot C into 1 plus F, because we have added fuel. So that is also straightforward. So if you plug in these numbers, what happens is what you will get is 3.24 kilowatt, which is around 3.24 megawatts, which is less than what we got in the flying condition. So ideally, in reality, you will not. So in most of the engines, typically you would see that in ground condition you will be generating more thrust. In ground condition you will be generating more power. But this is a special case here in especially for this engine, because of the parameters that we selected, and that is the reason we are getting a lower power in the ground condition. If not, we typically should get higher power in the ground condition. Okay, so please remember that it is not, you cannot generalize that ground condition will give more power and or vice versa, ground condition will give less power. Okay, so it depends upon the parameters, and you need to do the analysis to find out what is the power. Okay, and similarly you can find power delivered to the load, and that is nothing but 99% of 3.24 megawatts, which will be 3.207 megawatts. Okay, this is the power. The next performance parameter that we have is efficiency. So thermal efficiency, we can calculate it as the expected output is here is shaft power, and the input that we give in terms of fuel is m dot F into QR. So the shaft power we know it's 3.24 megawatts, and m dot F and QR we know. So if you substitute the numbers, you will end up having efficiency of 28.28 percentage, which is comparable to the flying condition, which was around 29.52 percentage. Okay, and the brake specific fuel consumption, again it's going to be based on shaft power. So previously in thrust specific fuel consumption, what we had is m dot F by T, right? Because thrust was our main goal out of the engine. Here it is going to be shaft power. So again, if you substitute 3.24 megawatts instead of SP, and m dot F is 0.0217 times 12, 12 is mass flow rate. If you substitute these numbers, you will end up having brake specific fuel consumption of about 0.08 grams per kilowatt second. Okay, so this is the um, fuel economy that we get from this engine at the ground condition. Okay, so if I substitute all these, if I collect all these things together, and if you put it here, the load or the power to the load or power from the pre-turbine is actually reduced from flight condition to ground condition. Okay, but it is not ideal, so everywhere it will not behave like this. Okay, and so let's say, for example, if I want to give you an idea what really happened, why we are getting lower power for ground condition. So what happened was, actually you can find it for yourself. So you can find what is the work you require for the compressor. So for example, let me put you. So work done by the compressor. Okay, and then pi high pressure turbine, and then pressure ratio of free turbine. Okay, so you compare these values for flight condition and also for ground condition. How different are they? Okay, and at the end of the day the power is going to depend on only this. Okay, in this itself some of them would be interdependent. Okay, so this is for at same pi c. Okay, this was same pi c for both flight condition, I mean the same engine. um, so uh, you should compare and contrast between these two conditions. What is the work done by compressor and what is the pressure ratio across turbine, both the turbines our engine is operating, and that will give you an idea what exactly happened with the ground condition. Okay, so uh, and also, yeah, you should be cautious that it is not true that always the ground condition will yield higher power, or in thrust always the ground condition will give you higher thrust. Okay, so you should be a little bit careful, and that is something I wanted to let you know. But otherwise it's a pretty straightforward numerical. I hope everyone can easily follow it. It's not a very big deal. And in the next week, what we are planning to do is, this is something we haven't done in the lectures. Okay, so of course, we have gone through component matching for turbojet engine, but we haven't gone through any numericals of it. And so, what we will do next week is we will try to solve a numerical and see how this component matching could be helpful, and what are some important insights that we need to obtain from this component matching exercise. Okay, so that is what we will do next week, and by that we will complete our course. Okay, and if you have any questions, I urge you to attend next week's class, and I will be available for entire 2 hour duration, and you can we will quickly go through this problem, and then you can ask your questions, clear your doubts. That should be helpful for your exams coming up. Okay, all right, so if you have any questions you can ask. I will be available till the end of this session till 9 o'clock, and if we don't have any questions we can meet on next week. All right, thank you Krishna for joining, and thanks everyone for viewing it from YouTube.